Hello everyone, and welcome back to Educator.com. I'm Dan Fullerton, and in this lesson we're going to start our study of kinematics, looking at the descriptions of motion. So our objectives include understanding the general relationships among position, velocity, and acceleration for the motion of a particle, using kinematic equations to solve problems of motion with constant acceleration, and that'll be carried over into the second half of our lesson, and writing an appropriate differential equation and solving it for velocity in cases when acceleration is a specified function of velocity and time. So, position versus displacement. An object's position is its location at some given point in time. The vector from the origin of the coordinate system to the object's position is known as the position vector, which is r. Sometimes you'll see it written as s. rs we're going to use interchangeably in here. As an object moves, its position changes. This change in position is called displacement, delta r, or it could be delta s. Position and displacement are both vectors. They have a direction as well as a magnitude. And in one dimension, position is given by the x-coordinate and the displacement oftentimes written as delta x. Okay, so a couple examples about the differences between these. A deer walks 1,300 meters east to a creek for a drink. The deer then walks 500 meters west to the berry patch for dinner, before running 300 meters west when startled by a loud, angry, fierce, nasty, evil raccoon. What distance did the deer travel? Well, the distance the deer traveled, 1,300 plus 500 plus 300, would be 2,100 meters. But what is the deer's displacement? That's how far it is from its starting point. So it went 1,300 meters east, 500 west, now it's only 800 meters east. And then it went 300 meters west, so it's 500 meters east from where it started. Delta x, its displacement, is 500 meters east. And because it's a displacement, it's a vector, it needs a direction as well. All right. Average speed is the distance traveled divided by the time it took to travel that distance. V with the line over it oftentimes depicts average speed, which is distance traveled divided by time. Average speed is a scalar and is measured in meters per second. The way I remember that, speed, s, is a scalar, s. If we look at velocity, on the other hand, velocity is the rate at which position changes, and position is a vector, so the rate at which it changes is also a vector, velocity. Now, average velocity is the displacement during a time interval divided by the time interval, not the distance. The displacement is average velocity. So average velocity is a vector, it has a direction, but it also has units of meters per second, and they're awfully easy to confuse because they get the same symbol v. Velocity, v, is a vector. Speed, s, is a scalar, s. Let's take a look. The deer walks 1,300 meters east to the creek, 500 meters west to the berry patch, before running 300 meters west when it's startled by that loud, evil, angry, nasty raccoon. The entire trip took 600 seconds, 10 minutes. What is the deer's average speed? Well, v average is distance over time. It traveled 2,100 meters was its distance over 600 seconds, so the average speed was 3.5 meters per second. The deer's average velocity, however, average velocity is delta x over t, which was 500 meters east, its displacement, divided by the time, 600 seconds, or 0.83 meters per second east. Notice how subtle these are in their differences. Average speed, you're worried about distance. Average velocity, you need displacement. Okay, let's do an example with our dear friend Chuck the hungry squirrel. Poor Chuck travels 4 meters east and then 3 meters north in search of an acorn. The entire trip takes him 20 seconds. Find how far Chuck traveled. Well, that's easy. The distance traveled is 4 meters plus 3 meters, which is 7 meters. Chuck's displacement, however, is a little trickier. Chuck traveled 4 meters east, then 3 meters north. Displacement the straight line distance from where you start to where you finish. So that's a 3, 4, 5 triangle. That must be 5 meters. So Chuck's displacement is 5 meters northeast. And if we wanted to, we could find the angle to be even more specific. That would be the inverse tangent, if we're calling that angle theta, of our opposite over the adjacent, 3 meters over 4 meters, which is about 36.9 degrees. Chuck's average speed, well, average speed is going to be distance divided by time, or 7 meters over 20 seconds, which is 0.35 meters per second. Chuck's average velocity, a little bit different, delta x over t, how far his displacement divided by time, which was 5 meters northeast over 20 seconds, which would be 0.25 meters per second, and it's a vector. It needs a direction, northeast. Subtle differences. You really have to know what you're talking about and read carefully when you get into distance, displacement, speed, velocity considerations. Okay, let's take a look at acceleration. That's the rate at which velocity changes. So acceleration is change in velocity over time. It's a vector, it has a direction, and the units of acceleration are meters per second, or meters per second squared. That can be confusing to a lot of folks the first time you see it. As velocity changes, you may go from a velocity of 10 meters per second to 20 meters per second. If that time it takes you to change your velocity by 10 meters per second is 1 second, you went from 20 meters per second to 10 meters per second to 20 meters per second in 1 second, your acceleration was 10 meters per second every second, or 10 meters per second squared. Now, as we're talking about the relationship to velocity, acceleration is the derivative of velocity with respect to time, or would be written as v prime. Okay, acceleration problem. Monty the monkey accelerates from rest to a velocity of 9 meters per second in a time span of 3 seconds. Find Monty's acceleration. Acceleration is change in velocity divided by time, so that'll be final minus initial velocity over time, which is 9 meters per second minus 0 meters per second, all in 3 seconds, or 3 meters per second squared. Okay, let's take a look at the position vector. If we have a path in space and we have a particle that's moving along that path, we could define its position at various points in time. Its first position at some time t1, we can define its position by a vector from the origin to that point. Let's call that the position vector at time t1. A little while later, it's over here at time t2. So we could define the position vector at t2 as such. There's its position vector at time t2. What happened between t1 and t2? That was when we had a change in position, delta r, which would be the position at t2 minus the position at t1, which we could define as going from that point to that point. There's our delta r. And while we're doing this, we can look at the position function as a function of time and realize that our x value changes as a function of time. So we have x of t in the I hat direction, in the unit vector direction along the x-axis, plus y value is a function of time in the y direction, the unit vector in the y direction, j hat. Or if you prefer, you could write this as x is a function of time for the x coordinate, y is a function of time for the y coordinate. And of course, you could extend that out to 3 dimensions as well. Then our average velocity vector is just going to be change in r over some time interval. So if we take that and go further into average velocity, we have a particle traveling along a path. Find the average velocity between 1 and 6 seconds. Well, the average velocity is our change in position divided by time. If we're looking in the x, that's going to be x minus x0 over t. Note that we're just traveling in one dimension. It's a time versus distance traveled graph, which is going to be our final value. It's at about 5 meters. Maybe that looks more like 6. Now we'll write it as 5. 5 meters minus 2.5 meters over the change in time, 6 seconds. Yeah, I'd say that's about 5. 6 seconds minus 1 second, or 2.5 over 5, which is going to be about 0.5 meters per second. Interestingly, though, we could also look at the slope here. If we go and we try and take the slope for those 2 points, we'll pick a couple points on our graph. Looks like an easy one to pick will be 0, 2. And I'll also go over here to 6 seconds and say that we're at 5. So our slope is rise over run, which is going to be 5 meters minus 2 meters over 6 seconds minus 0 seconds, or 3 meters over 6 seconds is 0.5 meters per second. The slope of the position time graph gave us the same thing as velocity. It does give you the velocity. Looking at instantaneous velocity, average velocity observed over an infinitely small time interval. As you make that time interval smaller and smaller and smaller until it becomes infinitesimally small, you get the instantaneous velocity, the velocity at that exact point in time. Instantaneous velocity is the derivative of position with respect to time. So, velocity as a function of time is the derivative of position with respect to time, or you could write that as x prime. If we wanted to know what the absolute instantaneous velocity was here at 3 seconds, we'd find the tangent to the curve, the slope, right at that point in time. If it's 2 meters per second is our slope, that's the instantaneous velocity at that point in time. Now, if we also have an xt graph, the area under a velocity time graph is the displacement during that time interval. So if we make this instead, we go to a velocity time graph. This shows our velocity as a function of time. The area under it, if you integrate that, the integral of velocity, or just find the area, that's your change in position for that time interval. Now, acceleration is the rate at which velocity changes. So acceleration is the limit as delta t goes to 0 of delta v over delta t. Like we said, we make that time interval shorter and shorter and shorter and shorter. Or it's the derivative of velocity with respect to time. And since velocity is the derivative of position, that's the second derivative of x with respect to time. And note that we write that as d squared x over dt squared. Not really squaring anything. This is talking about the second derivative. The derivative, and then to take the derivative of the first derivative. Or the average acceleration is delta v over t. So if we've got a velocity time graph, we could take the slope here, and I'd get something that looks kind of like this, I think. Take the slope at that point. If we take the slope of that line, the slope of the velocity time graph at a specific point, that'd be about negative 0.18 meters per second squared, which means that the acceleration at time t equals 4 seconds, right where that point lines up, would be negative 0.18 meters per second squared. The slope gives you the acceleration at that point in time. We can also look at some graph transformations. If you have a position time graph, and you take the slope, you can get a velocity time graph. Take the slope of a velocity time graph, you can get an acceleration time graph. Or going the other way, start with the acceleration time graph. If you take the area under the graph, you get the change in velocity. If you have a velocity time graph and you take the area, the integral, you get the change in position. So you can go from one graph to another based on what you're trying to find using slopes and areas, derivatives and integrals. All right, so velocity and acceleration in 2 dimensions. Our velocity vector is the limit as delta t approaches 0, as that time interval gets infinitesimally small, of delta r over delta t, or we wrote that as dr dt, the derivative of r with respect to time. And if r is in multiple dimensions, then that would be the x component, derivative of the x component in the x direction, plus the derivative of the y component in the y dimension for however many dimensions you might have, or in bracket notation, dx dt for the x, dy dt for the y. Acceleration, then, is the derivative of velocity with respect to time, which would be the second derivative of x with respect to t in the x direction, plus the second derivative of y with respect to t in the y direction, or in bracket notation again, d squared x over dt squared, comma, the second derivative of y with respect to t. All right, so you can keep expounding upon that for however many dimensions you need. Typically, we're going to be working with 2 and 3 dimensions in this course. All right, so let's talk a little bit more about derivatives. If we have some function x is a constant times t to some exponent n, the derivative of x with respect to t is that power n times your constant times t to the n minus 1, the basic polynomial derivative formula. We're going to be using that quite a bit, so let's practice for a second. The position of a particle as a function of time is 2 minus 4t plus 2t squared minus 3t cubed. Find the velocity and acceleration of the particle as a function of time. Well, velocity as a function of time is the derivative of x with respect to the time, or you could write it as x prime, or you might even see that written as x with a dot over it. That's going to be, well, I'm going to start at this side just because I like the bigger exponents first. That'll be negative 9t squared plus 4t minus 4. Now to find our acceleration as a function of time, that's the derivative of velocity with respect to time, or the second derivative of x with respect to time. Or we could write this as v prime, or v with the dot, or x double prime, or x with 2 dots. They all mean the same thing. But eventually we take the derivative of our velocity, and I would come up with minus 18t plus 4. All right, more examples. An object moving in a straight line has a velocity v in meters per second that varies with time t. According to this function, 3 plus 2t squared. Find the acceleration of the object at 1 second. All right, acceleration is just the derivative of velocity with respect to time, which is going to be, derivative of velocity is just going to be 4t. And since we know in this problem that t equals 1 second, acceleration is just going to be equal to 4 times 1, or 4 meters per second squared. For part B, determine the displacement of the object between t equals 0 and t equals 5 seconds. Well, we want to know the displacement, delta x. That's going to be the integral from t equals 0 to 5 seconds. We can start to use definite integrals here because we're given some limits on the time of our velocity with respect to time, which will be the integral from t equals 0 to 5 seconds of 3 plus 2t squared dt, which will be 2t cubed over 3. That looks right. Plus 3t, all evaluated from 0 to 5 seconds. And remember what this means. That means we're going to plug the 5 in for the t's first. So we would get 2 times 5 cubed over 3, plus 3 times 5, minus, and now we plug the 0 in there, but 0 cubed plus 3 times 0 is still going to be 0. So what I come up with here is delta x is going to be 5 times 5 is 25 times 5, 125 times 2 is 250 divided by 3 plus 15 is going to give us about 98 meters. 250, yeah. There we go, the displacement of the object between 0 and 5 seconds. Taking a look at another example, the velocity time curve for the tortoise and hare traveling in a straight line is shown below. We've got our tortoise here in orange, our hare in blue. What happens at time t equals 30 seconds? Well, interpreting these can get a little tricky, so let's take our time and go right through it. At t equals 30 seconds, it looks like the tortoise and the hare have the exact same value for speed. So tortoise and hare have same speed. How do you know the two have traveled the same distance at time t equals 60 seconds? Well, let's see. At t equals 60 seconds, if we look here, we're given a velocity time graph. If we want to know distance traveled, that's the area under the graph. So for the tortoise, that would be the area of this rectangle, which is 60 times 4, 120, 60 times 4, 240 meters. For the hare, it's the area of this triangle, which you can probably see visually is the same, or use 1/2 base times height. You can find that the area for the hare is 240 meters. So at t equals 60 seconds, the area under each curve is the same. So delta x must be the same. And what is the acceleration of the hare at t equals 40 seconds? Well, what I would do is I would go over here to t equals 40 seconds and take a look and say the slope of the line right there should give you the acceleration. Acceleration is the slope, or change in velocity over change in time. It looks like we are going from, the slope of that line is -8 meters per second over 60 seconds, which is -4 over 30, -2/15 meters per second squared. So that would be the hare's acceleration. All right, one last one. Which of the following pairs of graphs best shows the distance traveled versus time and speed versus time for a car accelerating down a hill from rest? All right, let's take a look at the first one. If distance and time, it looks like it's moving the same amount every time, and the speed is constant. If it's accelerating, that doesn't make any sense. Can't be A. Looks like the further it goes, its distance traveled for each unit time is getting bigger and bigger. The slope of this at the different points gives you your speed graph getting bigger at a constant rate. B looks like it's accelerating. Your speed is constantly increasing at a constant rate. This doesn't make sense because the slope of this doesn't match your speed curve. And same here, distance is increasing linearly while speed is going up quadratically. Gotta be answer B. All right, hopefully that gets you a start on describing motion. We'll go a little bit further with this in our next lesson, Describing Motion Part 2. Thank you so much for watching Educator.com, and make it a great day.